Alright, so in this video we're going to talk about some other particular little things about gases, mainly their speed, and also how gases don't always behave in the way that we imagine that they should behave. So in ideal situations, gases will behave in certain ways, but that doesn't always happen. So at high pressures and low temperatures, some parts of kinetic molecular theory, which is how gases should behave in ideal situations, are invalid. So one thing is that KMT says that volume of gases are negligible. And technically, yes, a gas will take up some space. It just takes up a very, very small amount of space compared to the container that you put it in usually. So we usually say that the volume of the gas is actually negligible. That's not always true. So when you have a gas and you pressurize it into a small space, like you push it closer and closer together, that space that it occupies actually becomes much more significant. So the particles do actually occupy some space. Another part of KMT, kinetic molecular theory, is that the forces of attraction are negligible. So you've got these gas particles are moving all over the place. They're not attracted to each other. They're not repelling each other. That's not always going to be the case. If you have a low temperature, that means less energy is going into those molecules. Those particles are actually going to be closer together, and because they're closer together than they normally would be, you're going to have some sort of forces of attraction or repulsion happening. All right, so real gases, the volume is a little bit larger than it should be. Okay, and so if you're calculating the volume, your volume might actually be larger than what you calculate it should be. Okay, so you would actually have to subtract out a factor to get the real volume, what it should actually be. Pressure will be lower. Okay, that's because those molecules are closer together, so those forces of attraction are actually pulling those molecules even closer together. So they're not colliding with the container as often. So if you were to calculate a pressure and there's some attractive forces between those molecules, you're actually going to see that the pressure is lower than what you would calculate. So if you were doing this and you were trying to get a more accurate calculation, you would have to add in a factor. So this equation, really, this is the ideal gas law combined with van der Waals equation. You will not have to do anything with this, okay? What you do need to know is how the volume and the pressure can be different under this situation. So if you are looking at a gas, okay, and at a low temperature and a high pressure, your volume is going to be larger than it should be. So if you go calculate the volume out, and if it's at a high pressure and a low temperature, you're actually going to notice that the volume is larger than what you actually calculated out. Pressure will be lower than the calculations say. And that's because the molecules, since they're exhibiting some forces of attraction to each other, they're closer together. They're not going to be colliding with the container as much, so the pressure will be lower. So this is the gist of it. Okay, under high pressure situations, so when you put the gas into a highly pressurized container and you have it at a very low temperature, the volume is going to be larger than it should be, and the pressure will be a little bit lower than it should be. All right, so the velocity of the gases is related to a couple of different things. It's related to mass of the gas and also the temperature. So U is the velocity of your gas, and you can calculate it with this equation. So you use 3 times R, and the R here is going to be this, okay? And you multiply that by the temperature in Kelvin divided by my molar mass. You're going to have this in kilograms. The molar mass will actually be in kilograms because when you look at this unit right here, the joule is actually this. Okay, so this is what a joule actually is. it's a kilogram times meter squared divided by second squared. So that's why your molar mass has to be in kilograms, and that's the reason. All right, so let's find the RMS, the root mean square speed of a chlorine gas. So that's just a fancy way of saying how fast is the gas going. So let's find the root mean square of the gas. So we know that speed is equal to this. All right, so let's see what else was given to us. So we were given a temperature in Celsius. So let's go ahead and convert that. We're dealing with gases. It has to be in Kelvin. So 80 plus 273 gives me 353. I know it's chlorine gas. Chlorine gas is a Brinkelhoff, which means it's diatomic. So the molar mass of Cl2 is 70 grams per mole. Well, I know because of the R here, I'm going to have to convert this to kilograms. All right, so kilograms. So 1 kilogram is equal to 1,000 grams. Okay, so you're going to get 0.07 kilograms per mole here. All right, so now I've got my temperature, I've got my molar mass, I have my constant. I can just simply plug it into the equation. All right, so 3 multiplied by 8.314 times 353 divided by 0.07. So 3 times 8.314 times 353. All right, so divide it out. You're going to get a very large number, but remember you need to take the square root. Don't forget to do that part. All right, so now you're going to get a speed that is equivalent to this. 354 meters per second. And then that's actually an okay speed for gas. So your chlorine gas is going to have a speed of about this, using that equation. All right, so now let's look at something different. Because more than likely you're going to be asked conceptual questions, not mathematical questions about the speed of gases. So here's a graph, and the graph here has number of particles on the y-axis and then the speed on the x-axis. So you go from a slow speed to a fast speed here, and what you have here is you have various gases, so you have different gases for each line at the same temperature and pressure. So you need to figure out which gas would be which gas. So we're going to compare the molecular mass. Okay, so the molecular mass, the larger it is, the slower your speed is. So this, if you have a large gas, it's going to move very slowly, and that kind of makes sense. It's intuitive. So the larger gas, the lower the speed. So we need to figure out which of these three gases is going to represent the heaviest, and then which is going to represent the lightest molecules. All right, so what you have here, why it looks like this, is it's giving an average for all of your particles, what their speeds are. So it's the root mean square. So that's why we have this hump right there. So we're looking at like basically the height or the maximum point of each little peak. All right, so we need to figure out which one will be the heaviest and which one will be the lightest. So remember, here in the x-axis we have speed. Well, the faster speed is over here. So the hump right here, the maximum point that has the fastest speed is this one. The one that has the slowest speed is this larger hump right here. So that means that the more massive gas is going to be this one right here because it's slower, and then the least massive gas is going to be right here. So it's going to be a lighter gas right there. All right, so let's look at this question. So which substance is going to move at a higher velocity at the same temperature. So you've got 4 gases that they're comparing. Carbon dioxide is about 44 grams per mole. This one's about 131. Oxygen gas is about 32 grams per mole, and then helium is 2 grams per mole. So when I look at this and I'm comparing these values, the fastest gas is going to be the lightest gas. So in this case, it's going to be helium. All right, so now which gas would have a higher amount of kinetic energy? All right, so and this is at 273 Kelvin. Well, we know that this one would have the highest speed. Okay, so when we're comparing speed is this. So the more mass of the gas, the slower the speed. Well, kinetic energy is equal to this. Okay, this is kinetic energy. But the thing is, you've got mass and velocity here. Well, you know if your mass changes, your velocity is going to change as well. Your kinetic energy is not going to be impacted by the molar mass. So this is actually it's a trick question. The gases are all going to have the same amount of kinetic energy because they're at the same temperature. And so the mass does not impact kinetic energy, it impacts speed. So the kinetic energy really depends on the temperature. All right, so let's look at something with temperature and speed. All right, so when I look at this equation right here, M is on the bottom of the equation. So if I have a bigger m, that's going to equal a smaller number here. So if you have a more massive gas, you have a slower gas. Since that value is under a square root sign, you have to take the square root of that factor to figure out what happens with the speed. So basically, if you know that your gas is 4 times as massive, so I have a gas that's 4 times as massive as something else. So I have the speed of some gas, and then I'm comparing it to another gas, and the gas is 4 times the mass of the other. Well, I know that that means that the speed is going to decrease. So if I'm if I'm trying to figure out how much faster or how much slower the gas is going to be, I need to take this factor and then take the square root of it because it's under a square root sign. So if I take the square root of 4, I get 2. That means that the gas speed would go down by a factor of 2. So if you're given a question where it says arbitrarily, you have a gas, you're comparing the gases, one is 4 times as massive as the other one, what can you say about the speed? Well, you can figure out that the speed would be half the amount of the other gas. Okay, so let's look at another kind of example. Let's look at temperature. Okay, so temperature here, since it's being multiplied in my equation, I know that the higher the temperature, the higher the speed. So if I have a higher temperature here, I'm going to have a higher speed. So that's going to lead to an increase in U. Well, if I look here, it's also being square, there's a square root sign over it. So that means if my gas, or if my temperature was 4 times as great as a different temperature, well, I know my velocity would go up, but let's say that's 4 times as great. I'm going to take 4, take the square root of that, and then I could say that the speed would be twice that than the other speed.